Hi, welcome to part two. So we're going to start looking at solution equilibrium or dynamic equilibrium. We're going to look at some solubility curves. We're going to look at solubility of gases. And so solubility of gases is much different than liquids and solids because now we have to consider pressure and the effect that pressure is going to have on that gas in a solution. And then we're going to look at all those different ways to talk about the concentration of a solution, molarity, molality, mass percent, and all that. That's what we're going to kind of cover today. Obviously, there's going to be a lot of calculations that would be associated with this material, so I do encourage you to join for the Zoom meeting, and then we'll be able to cover those calculations as well. Solution equilibrium. So when you first start to add a solid, and here we're going to look at aqueous solutions. So I have an ionic solid, in this case I have sodium chloride. I'm adding that sodium chloride to a beaker of water. At the initial point, there's no ions in solution yet. As that sodium chloride crystal sits in the water, the ions start to disassociate from the crystal and they are solvated by the water through these ion dipole interactions here. So this is your delta H mix. So I'm hydrating that ionic compound. If I am close to the point where I can't add any more sodium chloride into solution, we call that saturation. Once you get to the saturation point, you start to establish an equilibrium. Up to that saturation point, I can still dissolve more and more sodium chloride in solution, but I'm going to get to a point where I can't add any more sodium chloride, and I'm going to start to see solid at the bottom of that beaker. At that point I've reached saturation. I've also reached a point called solution equilibrium, or it's dynamic equilibrium. And it's called dynamic because you're continually having ions disassociate into the water and then reassociate into a solid. And so those rates are going to be equal to each other at dynamic equilibrium. So if I have sodium chloride, solid, let's say I add that to water. So I'm just going to write water over the arrow. I'm going to start forming ions in solution. So I'm going to note them here as aqueous. And so I can continue to add sodium chloride, and sodium chloride is very soluble in water. And so I can add a lot of that. But at some point I'm going to get to the point where I'm going to have too much solute and I'm going to stop being able to dissolve it. And so at that point, we would call that saturated. No more solute will go into solution. This is called the saturation point. When you're at the saturation point, you're really at a place that's also called dynamic equilibrium. This course, we're going to look at a lot of equilibrium, and so we're just kind of introducing it here, and then we'll come back to it after we go through kinetics. So in 2 more chapters, we'll come back to equilibrium. The equilibrium, a lot of chemical reactions are in equilibrium, meaning that you have this kind of back and forth. And so it's represented by this double arrow. Sometimes you'll see it that way. Most often you'll see it written this way, where you have a half arrow going forward and a half arrow going back. Sometimes you'll see it written this way. Sometimes you'll see it written this way. To be correct, it's really written this way, where you have this kind of half arrow here. So that indicates that I'm at some sort of equilibrium. My rate forward, so at dynamic equilibrium, I have a rate of dissolution. That's my forward direction. So I take sodium chloride, it dissolves in water. That's my rate of dissolution. This is how fast the sodium chloride is dissolving. So if it's really soluble and I'm mixing it, I can do things to affect the rate. That might be fairly quick. Once I get close to saturation point, this is going to start to slow down. And then I'm also going to have something called the rate of recrystallization. And that's the reverse. Here you have how fast sodium ions and chloride ions are reforming in a Cl. Solid. At equilibrium, these rates are going to equal each other. So once I've reached dynamic equilibrium, then these two rates here equal each other. So the rate forward is going to equal the rate in reverse at equilibrium. What that means is that you're not going to see a change. You're not going to see a change in what that solution looks like. So if you think about being below the saturation point, so if I'm below the saturation point, so I haven't reached saturation, then I'm only going to see rate of dissolution. So as I add more of this in, it's going to dissolve into ions. If I have a solution that's above the saturation point, for whatever reason, however I got it there, I'm going to be and the rate of recrystallization. So if I'm above the saturation point, then I'm going to start to see these come out of solution and form the solid. At dynamic equilibrium, it's going to look like everything has stopped. So I don't see a forward reaction, I don't see a reverse reaction. It looks stagnant to me. But what really is happening is you still have ions that are dissociating, but then at the same rate, you have ions that are recrystallizing. And so dynamic equilibrium is said to be dynamic because your reaction hasn't stopped, or this solvation hasn't stopped. It's just the two rates are equal to each other. As this dissolves, this reforms. And that happens only at the saturation point. If I'm below this, I'm unsaturated, then I'm going forward. If I'm supersaturated, I'm going backwards, but at the saturation, I have this special circumstance where the rate that I'm going forward equals the rate that I'm going backwards, and that's happening continually, but I don't see a change in my solution. So we have three terms that kind of introduced here. So one is unsaturated. So this is below the saturation point. And here, you're just going to see the rate of dissolution. Here I have sodium chloride solid going to sodium ions and chloride ions. I have supersaturated, and a supersaturated is above the saturation point. And that means that I have, these are typically unstable. You usually have to force this to happen. These are unstable. Artificially increase the saturation point to get something into a supersaturated state. So those are typically unstable. If you jostle them, if you add any sort of solid in there at all, it'll immediately trigger this rate of recrystallization. So now I have sodium ions plus chloride ions going to sodium chloride solid. So I'm going in reverse. At saturation, I'm at dynamic equilibrium. So no more solution will go in, and it's going to look like the reaction has stopped, but really this is going forward and this is going in reverse at the same rate. And so that is solution equilibrium. Okay, so if we go back to the slides here, this is a solubility curve. And these are really interesting from a couple of standpoints because they show some trends here. And this is a solubility curve for solids. Right, so ionic solids in particular, so we're dealing in aqueous chemistry here. And what you see is on the y-axis is the solubility. So how many grams of that solute can I get in a fixed amount of water? In this case, it's 100 grams of water. And then on this side is temperature. And what you see generally is as you increase the temperature, you're going to increase the solubility, so that here, if I look at potassium nitrate, KNO3 here, if I'm at 20 degrees and I have, let's say, 20 grams of solute, so I would come over here, 20 grams of potassium nitrate at 20 degrees, I'm below this line, so I'm unsaturated. As I start to increase and add more KNO3, once I get up to about 30 grams, now I'm at that saturation point. The only way I can get more potassium nitrate to go into solution is to heat it, right? So if I heat it up to 30, now I can get up to about 45 grams of potassium nitrate. I can shift that saturation point by increasing the temperature. There's one anomaly here, Ce2SO4, and this is a transition metal. And so transition metals are typically our problem children of the periodic table, and so they don't always follow our periodic trends. But as you can see here, when we look at group 1A metals, group 2A metals, even some of our heavier main group metals like lead and calcium, these are going to follow that general trend. So we can say more often than not, if you have an ionic compound that's going to go into solution, increasing the temperature is going to increase the solubility of that solid. Now, what happens if we have a gas? So if I have a gas, what would be some of the things that affect the solubility of a gas? Gases are affected by pressure. Unlike solids and liquids, which are not affected by pressure, gases are affected by pressure, and pressure has a significant effect on the solubility of a gas. And so if we're thinking about gases and the solubility of gas, we have to be able to also consider pressure in that scenario. So here is a cold soda pop and a warm soda pop. I love this old school language here. No one calls them soda pops anymore. Anyway, so if I look at the solubility of gas, and in this case, my gas is CO2, carbon dioxide. As long as I haven't opened this can, CO2, which is a gas, is going to remain in the liquid. And the liquid is caramel coloring and a whole bunch of other junk and sugar and lots of sugar, right? In the soda is a lot of stuff in the liquid phase, and then carbon dioxide is a gas that's in solution with that liquid. And so as long as it's under pressure, meaning that there's a pressure that's pushing down on the top of that liquid, it's going to keep CO2 in the solution. The minute I open that can and I depressurize it, now I've reduced the pressure that's on the surface of that liquid, and carbon dioxide can escape that solution. If I heat it, this process is going to happen even faster. So if I have cold soda and I open it, CO2 is going to escape less quickly than if I have warm soda. I have it sitting on the counter and I open it, then the carbon dioxide is going to escape much easier. So I have to consider, if I look at the solubility of gas, I have to consider not only temperature, but also pressure. And unlike solids, the solubility of a gas is inversely related to the temperature. So the colder the temperature, the more soluble the gas. The higher the temperature, the less soluble. And that's because gas molecules have high kinetic energy. So when you heat a gas, what happens? That gas starts moving faster. If it's in a solution, it's going to move more so that it can break free of the surface of the solution and escape into the atmosphere, into the gas phase. And so when I look at gases, I have to specifically consider temperature and pressure. And that brings us to our first equation for this chapter. And this is called Henry's Law. And it only applies to gases. Big S, now we're not talking about entropy. This is big S, a different big S, K of a gas, and P of a gas. And so let's define what these things are. This here is the concentration of the gas in molarity, big M. Big M, remember, has units of moles per liter. Okay, so that's going to be my concentration of my gas in units of molarity. K is called Henry's constant. And this is a constant that's unique to the gas. So there's not just one value for K, there's a value for K that's dependent upon the gas. And that has units of molarity over atmosphere. So those are your units of Henry's constant. And so this is where your molarity term is going to come from. And then P is my partial pressure of my gas, and it is in units of atmospheres. So when I multiply this by this, the atmospheres are going to cancel and I'm left with units of molarity. So that's how my solubility here can be in units of molarity. So my solubility is, if you can see from this equation, is that the solubility is directly proportional to the partial pressure of the gas. So the solubility of the gas is directly proportional to the partial pressure. Meaning, the higher the partial pressure of that gas, the more solubility there is. And does that make sense based on what we know about gases? If you remember back to the chapter where we talked about gases, we had this equation here, that gases behave ideally, and I can look at the partial pressure of gas A by considering the mole fraction and the total pressure. So this is from earlier chapter. So these are two equations that it's going to be important when you're dealing with gas that you guys remember for this chapter. So here, this is my partial pressure of my gas. This is my total pressure of my mixture of gases. And this is the mole fraction of my gas. And in this case, gas A. And if you remember mole fraction would be number of moles of A over total moles in solution. So mole fraction is unitless. So whatever your units are of your total pressure, those are going to be the same as your units of partial pressure. But when you pull this into here, it needs to be in atmospheres. Okay, so let's look at some of these constants that we have for Henry's law. Here is a table, and what you see here is O2, N2, CO2, NH3, helium. These all have very different constants for Henry's law. So this would be not something that you would be required to memorize, but just if you were given an equation where you're solving for the solubility of a gas or the partial pressure of a gas given the solubility, you would want to refer back to this table, and this is a table that's in your textbook, to see what the constant is if it wasn't given to you. So that's Henry's law. The last thing I want to cover is all the various ways, and like I said, we'll do some problems with Henry's law when we meet together in our Zoom session. We'll do some problems with that. The last thing I wanted to talk about was all the various ways that we have of doing concentrations for solutions that don't involve gases. And there are a lot of ways, and we're not going to obviously cover them all, but there are a lot of ways to think about how we would talk about concentration, which means how much solute per solution. So how much solute per solution, that's going to be our concentration. So the more concentrated something is, the more solute you have in that solution. The less concentrated, the less solute you have. Okay, there we go. So concentrations for solutions that don't involve gases. All right, so we have a lot of different ones. So I'm going to actually need more space. So I'm going to get a fresh piece of paper here. Okay, so my type here, so these are solution concentrations. I'm going to look here. This is going to be my type. This is how I'm going to name it. This is going to be the definition. And then I'm also going to look at my units here. And I can take a solution and I can give you a value for the concentration that can be different. So I can give you a mass percent value, and that would be grams of solute. We'll do solute in blue. Solute over grams of solution. And since it's a percentage, you would multiply by 100. So my units here, because my grams are going to cancel out, my units are going to just be percentage, because my grams of solute cancels out with my grams of solution. So that's mass percent. Volume percent, and oftentimes you'll see this written as mm and volume as VV, just to note that your units are going to be different. This is milliliters of solute. So notice solute's always in the numerator over milliliters of solution. And it's a percentage, so I'm going to multiply by 100. That means my units for this are going to be percentage. I can also have mass volume percent. And here I have mass over volume, so grams of solute over milliliters of solution times 100. And this also is going to give me units of grams per milliliter percent. So now my units don't cancel out. If you see something where you see ppm by mass, that means you have parts per million, or ppb by mass, then I have parts per billion. These look very same to mass percent. Instead of multiplying by 100, you multiply by 10 to the 6th or 10 to the 9th. So this would be grams of solute over grams of solution times 10 to the 6th. That's where your million is going to come into play. Your units of this are going to be ppm would be our units. If I have ppb, still same thing, grams of solute over grams of solution. But now instead of times 10 to the 6th, I'm going to do 10 to the 9th for billion, and then my units of that would be ppb. And I can do the same thing. I can have parts per million by volume and parts per billion by volume, and then the difference is down here, this is going to be, your units are going to be different. These things here are always called your multiplication factors. Multiplication factors. Do I multiply by 100, then I get percent. Do I multiply by 10 to the 6th, then I get parts per million. If I multiply by 10 to the 9th, I get parts per billion. Okay, so that's one type. The next type, which we use more often in, especially in aqueous solutions, is molarity. and that's big M, and that's moles of solute over liters of solution. This does not have a multiplication factor, and so my units for this are moles per liter. So this is not a percentage. I have big M here. The next one is molality. And molality and molarity look similar, but molality is little m. So I try to do a cursive in there. In molality, I have moles of solute over kilograms of solvent. And so this is the only time where I have solvent solely by itself. Everything else has been solute over solution. So my units of this are going to be moles per kilogram. And molality we're going to use in this chapter for particular types of problems that we're going to look at. And then the last one was one that we just talked about, was mole fraction. Moles of solute over moles of solution. And there's no units here. And then mole percent. Mole percent you don't see very often. Mole percent is just X times 100 to give you percentage. So I would take my mole fraction and multiply it by 100. So those are all the various ways that we can look at concentrations of a solution. I'm just going to pull up the slide here. And there's a slide in your book, table in your book, that also works all this out. Okay, so here you see molarity, molality, mole fraction, mole percent, and then these are all those ones that we started with. All right, so we will end there, and this concludes all the material we're going to cover, and then we're going to start talking about colligative properties and vapor pressure and all kinds of new stuff that you haven't been exposed to yet. Okay, so I hope to see you in our Zoom session. Make sure that you're following along and working through the problems as well.